Hello. Now we're going to be looking at the ultrasound transducer, which generates and receives the ultrasound pulses. And we're going to look at the ultrasound beam and how that is focused. Let's talk first about the transducer. This is the component in the probe which creates transmitted ultrasound pulses and receives the returning echoes and converts those into electrical signals. The transducer is made of a piezoelectric material, which means that when pressure is applied to it, it generates a voltage. If that is a time-varying pressure, then there will be a time-varying voltage. Originally, ultrasound transducers were made of a ceramic material, and those ceramic materials were actually developed during the Second World War for sonar purposes. They've become largely obsolete in the field of diagnostic ultrasound now because they inherently have a fairly narrow range of operating frequencies. So now other materials are used, and often the transducers are what are referred to as composite transducers, and these operate over a far wider range of operating frequencies. So in the past, transducers may have been referred to as 5 MHz transducers or 3 MHz transducers. But now you're more likely to have a transducer that will operate from 3 MHz up to 8, for example, or 5 up to 12. So you get a wide range of operating frequencies in any one probe. On the left, we have a diagram showing the transducer transmitting ultrasound. So the transducer is a thin strip of material, typically about less than 1 millimeter in thickness. It has metallic coatings on the front and back surfaces. So these then allow wires to be connected so that the machine can apply voltages to the transducer and can receive voltages which it generates when it is receiving ultrasound. So on the left we have the transducer transmitting ultrasound. A time-varying electrical voltage is applied to the transducer. This causes its thickness to vary, and that transmits itself into the tissues as varying pressures. And so we get an ultrasound pulse, which has a wave shape identical to the applied voltage, and that travels through the tissues. On the right-hand side, we have a diagram showing what happens when the transducer is receiving ultrasound echoes. Those ultrasound echoes consist of pressure variations. So these pressure variations affect the transducer, setting it oscillating in thickness. Now they're very small amplitude, and therefore the thickness variations of the transducer are going to be very small. But nevertheless, this generates a voltage which is exactly equivalent to the ultrasound pulse. And so we get an electrical signal that exactly matches the received echo, and this can be received by the machine and processed to produce, eventually, an ultrasound image. This diagram shows us roughly what you'd find if you cut a probe through and looked at it in cross-sectional view. So I've drawn a linear probe sitting on the skin surface. The grey strip of material is a view of the transducer material, and we're looking at it edge on, remember, so that's going to be less than 1 millimeter in thickness. You'll see that in front of the transducer material we have what I've shown as a green material, and this is labelled matching layer. The purpose of this is to match the transducer to the tissue to improve the free flow of energy between the transducer and the patient's tissue. This is needed because the transducer material is very different to tissues, and therefore it has a very different acoustic impedance. So basically the matching layer acts as a kind of translator between the transducer and the tissues. It operates both in transmitting and receiving to minimize the effect of the acoustic impedance difference between the transducer and the tissues. Now when the transducer vibrates, it can transmit energy into the patient's tissues, but equally into the body of the probe. We don't want transmitted ultrasound in the body of the probe because that could reflect around and create echoes that the machine would think had come from the patient's tissues. So the backing layer that I've shown here is simply there to absorb energy that would otherwise be transmitted into the body of the probe. The other thing that I'm showing in this diagram is the electronics in the probe. This, as we'll see later on, is used to select different parts of the transducer to operate as transmitter and receiver at various times. Now we're going to look at the way in which the machine focuses the ultrasound beam and the nature of that beam. You'll notice on the right-hand side that I've drawn a focused ultrasound beam. I've marked two important parameters: the size of the transducer, which we refer to as the aperture, A, and then the depth of focus, which is the depth at which the beam is actually being focused, which is going to be the narrowest part of the beam, and I've labelled that F. Now you'll notice a pair of broken black lines here, and these are what's called the diffraction limit, or these define the diffraction limit. As the name suggests, the word limit, this limits just how well the beam can be focused. The narrower the diffraction limit is, the narrower the beam can be made. Let's have a look at the geometry of the diffraction limit on the left-hand side here. Again, I have labelled the size of the aperture, A, and you'll notice the diffraction limit is simply a pair of straight lines diverging at a constant angle relative to the centre of the beam, and I've called that angle theta. Down below we have an equation that defines or allows us to calculate this divergence angle, and it says simply that the sine of the angle is equal to 1.22 times the ultrasound wavelength divided by the aperture size. Now, we would like the diffraction limit to be as narrow as possible, because that means the beam can be focused and be made narrow, and this is going to improve the resolution of the image. So what do we need to make the diffraction limit as small as possible? The answer is we want the wavelength to be as small as possible. And this, of course, is achieved by making the frequency as large as possible. So we want to use the highest possible frequency that we can, consistent with the depth of penetration we require in the clinical setting. So we use as high a frequency as possible and make the wavelength as small as possible. The other parameter then is the aperture, the size of the area on the face of the probe which is transmitting and receiving the ultrasound. And you'll see that the sine of the diffraction angle is proportional to 1 over the aperture. This means the larger the aperture is, the narrower the diffraction limit will be, and therefore the better the focusing. So we basically want high frequency and a large aperture, and that will give us the best possible focusing. Going back to the right-hand side now, we see that the ultrasound beam is wider than the diffraction limit up until the point where we get to focus, and at that point the beam touches the diffraction limit. So it's wider than the diffraction limit, and then at focus or around focus it touches the diffraction limit, and then at greater depths it spreads out again and is wider than the diffraction limit. So the diffraction limit is basically defining the width of the beam in the focal region. And because we can calculate the diffraction limit, we can calculate the beam width in the focal area. And that's what I'm showing here on the right, that the beam width is equal to 2.44 multiplied by the wavelength, multiplied by the depth of focus, divided by the aperture. So we see, as I've already mentioned, that the beam width will be narrow if we can have a small wavelength and a large aperture. But notice the other thing is that the beam width at focus is proportional to the depth of focus. So if I focus at a depth of 1 centimetre, I can focus very strongly and have a narrow beam. If I'm focusing at a depth of 20 centimetres, the beam width at focus is going to be larger because I'm at a much greater depth. This is just an unfortunate fact about focusing, that when we're focusing close up, we can get very high resolution. When we're focusing in deeper, we are just forced to get poorer resolution because of the depth, and also, of course, because we'll be forced to use lower frequencies to get to that depth. So inevitably, ultrasound images obtained when the probe is close up to the tissues are going to have higher resolution than ultrasound images obtained from deep tissues. There is just no escaping this. Now I want to introduce a couple of concepts that help you to understand how ultrasound machines actually focus the ultrasound beam. This one relates to the way intensity varies at different depths within the ultrasound beam. So let's first define what we mean by that beam. We mean the pathway that the ultrasound travels within. So when I talk about the transmit beam, I mean that defines the pathway that the transmitted ultrasound energy travels along. So the transmitted ultrasound is basically constrained to be within this beam, and therefore the beam defines exactly where the ultrasound will be interacting with the tissues. Now the intensity, which is the particular thing we're interested in here, just as a reminder, that is power divided by area. So if I have a certain amount of ultrasound energy per second, that's what we call power. So there's a certain amount of power being transmitted by the machine and traveling along this beam. We'll ignore attenuation and just imagine that that power travels along the beam unchanged from the probe face to the deeper tissues. Again, as I said, what we're interested in is intensity. So that's going to be the power divided by the area of the beam. And that's where things get interesting. In the focal region, the beam is narrowest, and therefore the area is small. So the beam is narrow, the area is small, therefore the intensity will be high. You may, as a child, have played around with focusing the sun's energy using a magnifying glass onto some paper or a leaf or something like that, and actually burning that object. And that's because you get extreme intensity if you focus the sunlight into a very small dot. So it's the same idea here, that the narrower the beam is, the greater the ultrasound intensity will be in that focal region. In other areas, closer to the probe and deeper in, where the beam is larger and therefore the area is bigger, the intensity will be lower. So we've got a certain amount of power traveling in this beam. The intensity varies depending on the area of the beam. At the focal point, the area is smallest, therefore the intensity is highest. This is particularly interesting to us because it works in reverse. If the machine can do things which make the intensity at a particular depth the maximum possible, the highest possible intensity, that's going to guarantee that the beam is as narrow as the machine can make it at that particular depth. So that's basically how focusing works. At the depth you want the beam to be focused, the machine is going to strive to make the intensity as high as possible, and that's going to guarantee that the beam is as narrow as possible. Huygens' principle was first proposed, of course, in the context of light and talking about the focusing of light. So we do the same thing in ultrasound. In order to figure out what's going on in the tissues when we transmit energy from a transducer, we have to find some way to make that a manageable problem. And the way we do it is to follow Huygens' principle, which says, let's think about each individual point on the face of that transducer and think of it as independently sending out ultrasound waves into the tissue. So we've basically got all points across the face of the transducer, or at least the active part of the transducer, transmitting ultrasound energy at the same time, each of them individually causing its own transmitted energy. Now, if we were transmitting ultrasound from a small point, it would spread out in all directions. There would be absolutely no beam. It would be very much as if I had dropped a stone into a pond of water, and we would just get a series of ripples spreading out equally in all directions. So you can think of each individual point on the transducer face creating ultrasound energy that travels out through the tissues in all directions equally. Somehow, when we have an area, rather than just a single point transmitting, but we have a whole area, which we call the transducer, then the ultrasound forms a beam. And it's a rather extraordinary thing. And the same, of course, is true of light. And so basically the idea is that within the beam, the transmitted energy from all the different points on the face of the transducer adds together in a way we call constructive, and that creates a significant amount of ultrasound energy. In the areas outside the beam, the energy traveled from the different points on the face of the transducer tends to cancel out, giving virtually no energy at all as the net result. So it's the interaction of the ultrasound from all these points across the face of the transducer that generates a beam. So let's talk about the way in which ultrasound transmitted from different parts of the transducer can add together within the tissues. On the top left, I've got what we could think of as maybe the ideal situation, which is where the energy transmitted from two different points on the transducer arrive simultaneously at a given point in the tissue. And we call this in phase. So the transmitted ultrasound from two different points on the transducer is arriving at this particular point in the tissues in phase. It's then going to add up to give us an ultrasound wave of twice the amplitude. So it's going to give us the strongest possible sum of those two individual transmitted pulses. So this is how we maximize the intensity at a point. We make sure that the transmitted pulses from different points on the face of the transducer arrive at the same time. Down below that, we have the opposite situation, where the transmitted energy from two different points on the face of the transducer arrives 180 degrees out of phase, or in opposite phase, which means that basically these waves are half a cycle apart in their timing. So when one of them is trying to increase the pressure, the other is equally trying to decrease the pressure. And not surprisingly, they cancel one another out, and the net result is 0. So to repeat, on the top left, we've got two pulses from two different parts of the transducer arriving simultaneously in phase, creating the maximum possible intensity. Below that, we've got two pulses arriving half a cycle apart in timing, completely cancelling out. On the right-hand side of this diagram, I'm showing an in-between case where the two pulses arrive a quarter of a cycle apart in timing, and that gives us a lower amplitude net result. So the main thing is what I'm showing on the top left, that we want contributions to the ultrasound from different points on the face of the transducer to all arrive at the focal point at the same time, because this will maximize the intensity at that focal point. Now let's think about geometry. Suppose I have a linear probe, and I am transmitting from different points on the face of that transducer, and I want to focus at the point I've labeled P. If I transmitted from every point on the face of the transducer at the same time, the ultrasound would travel along different paths to get to the point P. And I've labelled these path lengths D1, D2, D3, etc. Now we come to some simple geometry. The length D1, the distance D1, is the shortest of these paths. So the ultrasound transmitted from the centre of the transducer will arrive first at the point P. D2 and D3 are a bit longer, and therefore the ultrasound energy transmitted from those points on the transducer will arrive a bit later at the point P. And finally, the path lengths D4 and D5 are the longest of all, and the ultrasound transmitted from those outer edges of the transducer will arrive substantially later at the point P than the ultrasound from the other points on the transducer. So we're basically not getting the ultrasound arriving at this point P simultaneously. Quite the reverse. We're getting it arriving at different times from every point on the face of the transducer. Obviously, we can't focus the energy at that point P because we can't maximize the intensity there. The only way to deal with this, or at least the way in which ultrasound machines do deal with this, is to break the transducer up into a large number of little bits and transmit with each of those little bits at a slightly different time. And the timing is organized so that the pulses from each of those transducers, those little pieces of the transducer, will arrive at the point P at the same time. So that basically means we need to chop the transducer up into lots of little bits, and we refer to that as an array transducer. So that's the basis of how the ultrasound machine is going to focus, and we'll look at that in more detail in the next talk. So in summary, I've talked about the transducer, the fact that it uses piezoelectric materials to both transmit and receive ultrasound, converting an electrical pulse into transmitted ultrasound, converting a received ultrasound pulse or echo back into an electrical signal. I've shown you very quickly the probe construction and the need for a matching layer between the transducer and the tissues to deal with the acoustic impedance mismatch between them. I talked about the diffraction limit and how that defines the width of the ultrasound beam at focus. I then talked about a couple of things that relate to how the machine does the focusing. First, the variation of intensity with beam width, and the fact that if we maximize the intensity at a particular depth, that's going to guarantee the beam width is minimized at that depth, and that's what we mean when we say focus. Talked about the Huygens principle and the principle of superposition, and the fact that these lead us to the need to cut up the transducer into many small parts, which we refer to as an array transducer. So that's going to lead us into a discussion in the next talk of just how the machine actually focuses for both transmitting and receiving.